Right now, as you're watching this video, light from the sun took 8 whole minutes to reach your eyes. But here's what will absolutely blow your mind. Light is simultaneously the fastest thing in the universe, and it's impossibly slow. I know that sounds like a contradiction, and that cognitive dissonance you're feeling right now? That's exactly where we need to start. Think about it this way. Light can circle the Earth 7.5 times in a single second. 7.5 times. That's faster than you can blink, faster than you can think, yet. Einstein looked at this number and said, actually, that's the cosmic speed limit. Nothing can ever go faster. And he was right. But not for the reasons you think. Before we blow your mind completely, I need you to do something for me. If you're watching this right now, whether it's morning, afternoon, night, or somewhere in between, I want you to tell me in the comments what time it is, where you are, and what country you're watching from. I'm genuinely curious about the global community that's about to have their understanding of reality fundamentally shifted. Seriously, drop it in the comments. And if you are the type of person who gets excited about discovering hidden truths about our universe, smash that subscribe button right now. We've got 14 mind-bending sections ahead, and trust me, by the end of this video, you're going to see the world completely differently. Let me establish the foundation here, because the speed of light is so fundamental to everything we're about to discuss. Light travels at 299,792,458 meters per second. That's not an approximation. It's the actual number, and it's so precise that scientists have literally redefined the meter based on this number. Here's your first mind-blown moment. The speed of light isn't actually about light itself. It's about the speed at which cause and effect can travel through the universe. Albert Einstein didn't discover the speed of light. In 1905, scientists had already measured it. What Einstein discovered was something infinitely more profound. He realized this number represents the fundamental speed limit of reality itself. Think of it like this. Imagine the universe is a game, and c, that's what physicists call the speed of light, is the frame rate. Nothing can move faster than the frame rate of reality. Einstein figured out that this isn't just a coincidence. It's the foundation of how space and time themselves are constructed. Now, before Einstein, everyone thought space and time were these fixed, absolute things. Isaac Newton believed this. Galileo believed this. For hundreds of years, humanity assumed that time flows at the same rate everywhere, for everyone, always. That space is just an empty container where things happen. But in 1905, a 26-year-old patent clerk in Switzerland would demolish this entire worldview. Einstein showed that space and time are woven together into something called space-time, and the speed of light is the weaver. This is where things get weird. The speed of light is constant for every observer, no matter how fast they're moving. Let me repeat that because it sounds insane. If you're standing still and a spaceship zooms past at 90% the speed of light, you both measure light traveling at exactly the same speed. That's not supposed to be possible, but it is. And that impossibility is the key to understanding everything. I know your brain is starting to feel weird right now, and that's perfect. That means you're ready for what comes next. But before we dive deeper, I want to give you a preview of the mind-bending concepts we're about to explore. In the next section, we're going to talk about something called time dilation, where time literally moves at different speeds for different people. Then we'll explore how nothing with mass can ever reach the speed of light, no matter how much energy you throw at the problem. Then it gets really strange. We're going to talk about how light can be trapped, frozen, and even made to go backwards. And finally, we'll explore the deepest implication of all the speed of light proves that your future is already written, and you might not have as much free will as you think. But first, subscribe if you haven't already, because the next section is where things transform from interesting to absolutely reality-shattering. Stay with me. What if I told you that time is not the same for everyone? Right now, Time is moving at a slightly different rate for me than it is for you. If I'm moving faster through space, time moves slower for me. If I'm standing still, time moves faster for me. This isn't philosophy. This is measurable, testable, observable reality. Scientists have proven it thousands of times. And here's the kicker. The effect is always the same cause velocity and gravity warp the passage of time. This is the second mind-blown moment. The faster you move through space, the slower time moves for you. Einstein called this time dilation, and he proved it mathematically. But it took scientists decades to actually measure it because the effect is tiny at normal speeds. You'd need to go incredibly fast to notice the difference. In 1971, scientists Joseph Haffel and Richard Keating performed an experiment that would change everything. They took atomic clocks, the most precise timekeeping instruments ever built, and put them on commercial airplanes. They flew around the Earth in opposite directions and came back. When they compared the clocks to reference clocks on the ground, the moving clocks had aged less by a measurable amount. Time had literally moved slower for them. Think of it like this. Imagine you and your identical twin live on Earth. Your twin takes a spaceship and travels to a nearby star at 99.5% the speed of light. They're gone for what feels like 2 years to them. But when they return to Earth, 100 years have passed here. Your twin has barely aged while you and everyone you've ever known have been dead for decades. This isn't science fiction. This is the direct consequence of Einstein's math. But here's what makes it truly mind-bending. There's no contradiction here. From the traveling twin's perspective, THEY are stationary, and the Earth is moving away from them at 99.5% the speed of light. So shouldn't they experience time passing faster? Both perspectives are equally valid. And yet, when they meet up again, the traveling twin is younger. One perspective must be correct. The answer is acceleration. The traveling twin had to accelerate to reach high speed. They had to decelerate to turn around. And they had to decelerate again to land back on Earth. Acceleration breaks the symmetry. The traveling twin is in an accelerating reference frame, and that's how we know which twin is really moving. Physicist Paul Langevin formalized this in 1911, and it became known as the twin paradox. But it's not actually a paradox. It's a profound truth about the nature of time. Time is not a river flowing at the same rate everywhere. It's a dimension that bends and stretches depending on how fast you're moving through space and how strong the gravity is around you. Here's the thing that gets me every single time I think about this. Right now, at this very moment, time is moving slower for astronauts on the International Space Station than it is for you watching this video. They're moving at 17,500 miles per hour around the Earth. It's a tiny difference. They age about 0.007 seconds less per 6 months than people on the ground, but it's real. We measure it. We account for it in GPS satellites, because if we didn't, your GPS would be off by several kilometers within a day. The speed of light is the fundamental constant that determines how much space-time warps. Faster speed equals more time dilation. Stronger gravity equals more time dilation. Einstein united these two concepts into his theory of general relativity in 1915, showing that gravity and acceleration are actually the same thing. Gravity isn't a force pulling you down. It's space-time being curved by massive objects. Your head might be spinning right now, and that's exactly where we want you. Time dilation is just the beginning of how the speed of light warps reality. In the next section, we're going to explore something even stranger: length contraction. Objects get shorter the faster they move. Not just appear shorter, actually shorter. Then we're going to talk about why nothing with mass can ever reach the speed of light, and that limitation will lead us to the most terrifying implication of all. That causality might not be what we think it is. But before we get there, I need to know, are you still with me? Drop a comment saying light speed if your mind is getting blown. And if you're not subscribed yet, what are you waiting for? This is the kind of content that fundamentally changes how you see reality. Here's a question that sounds stupid until you really think about it. If nothing can go faster than light, how do we know? How do we know that's actually the limit? The answer comes from the equations themselves. When you plug in the speed of light into Einstein's relativistic mass formula, something extraordinary happens. Mass increases as velocity increases. It's not a huge effect at normal speeds. If you're driving a car at 100 miles per hour, the relativistic mass increase is utterly negligible. But as you approach the speed of light, the mass increase becomes dramatic. At 90% the speed of light, an object has 2.3 times more mass than normal. At 99% the speed of light, it has 7 times more mass. At 99.9% the speed of light, it has 22 times more mass. And the closer you get to light speed, the worse it gets. The curve becomes asymptotic. It approaches infinity, but never reaches it. To accelerate an object to exactly the speed of light would require infinite energy. And there's only a finite amount of energy in the entire universe. The mind-blown moment, 26 to 28 minutes. But that's not even the strangest part. Along with relativistic mass, something else happens. Space contracts in the direction of motion. This is called length contraction, and it's the third mind-blown moment in this series. Imagine a spaceship is traveling past Earth at 99% the speed of light. On the spaceship, everything looks normal to the astronauts inside. But from Earth's perspective, the spaceship is contracted. It looks shorter. Not just a little bit shorter, about 7 times shorter. If the spaceship was 70 meters long on the ground, it would look only 10 meters long as it zoomed past. Think of it like this. Imagine you're watching a train zoom past at nearly the speed of light. From your perspective, the train gets squished. The cars are shorter. But here's the really wild part. The people inside the train don't experience any squishing. To them, everything is normal. They might measure the train at 70 meters, but you measure it at 10 meters. You're both right. Your measurements are both true. This is a genuine feature of reality, not a trick of observation. Physicist George Fitzgerald proposed this idea in 1889 to explain an experiment that puzzled everyone. In 1887, Albert Michelson and Edward Morley performed an experiment with light and mirrors, trying to measure Earth's motion through the luminiferous ether, a substance everyone thought filled all of space. The experiment should have detected Earth's motion, but it didn't. The results were 0. This null result was the most important physics experiment in history. Fitzgerald suggested that maybe objects contract in the direction of motion, which would explain why the Michelson-Morley experiment couldn't detect Earth's motion. He was right. Not because of the ether that doesn't exist, but because of space-time itself. Later, Hendrik Lorentz developed the mathematical transformations that describe how space and time change when you move at relativistic speeds. Einstein unified all of this into special relativity, showing that length contraction and time dilation are two sides of the same coin. They're both consequences of the fact that the speed of light is constant for all observers. Here's what ties this all together. If you're moving at 99.9% the speed of light, not only do you experience time dilation, time moves slower for you, but space actually contracts in your direction of motion. From your perspective, the distance to your destination gets shorter. A journey to a star 10 light years away. At 99.9%, the speed of light wouldn't take 10 years for you. Because of length contraction, the distance is much shorter from your perspective. And because of time dilation, time passes much slower for you. The combination of these two effects means you could potentially reach distant stars without waiting extremely long from your perspective. But, and this is critical, but you can never actually reach the speed of light. As you accelerate toward it, relativistic effects become more and more pronounced. Your mass increases, requiring more and more energy to accelerate further. The energy requirement approaches infinity as your velocity approaches the speed of light. The speed of light is the asymptote of the velocity graph. You can get arbitrarily close, but you can never reach it. This is where the universe laughs at our ambitions. We want to build faster ships, travel to distant worlds, escape to the stars. But the universe has written a law into its very fabric. The speed of light is the cosmic speed limit, and nothing with mass can reach it. Not because the universe is mean, but because the mathematics of spacetime itself forbids it. Now, you might be thinking, okay, so light is the fastest thing, and nothing can catch it. Got it. What's the big deal? The big deal is about to get exponentially bigger. In the next section, we're going to explore something that sounds impossible. How to slow light down, how to stop it, and how to make it go backwards. Light has always seemed like this pure, untouchable thing that travels in straight lines and nothing can change. But scientists have discovered ways to manipulate light in ways that seemed impossible just decades ago. And when you understand how light can be trapped and slowed, you'll understand something profound about the nature of matter and energy itself. Stick with me. We're about to discover that light is far weirder than we've ever imagined. And drop a comment if you want us to make a follow-up video on quantum mechanics, because what light can teach us about the nature of reality will blow your mind in ways we haven't even touched on yet. What if I told you that scientists can slow light down to a standstill? That they can trap light inside a medium and make it crawl along at a fraction of its normal speed? In 2001, physicist Lean Howe did something that seemed to violate everything we know about light. She slowed light down to 17 miles per hour. That's slower than a bicycle. Light, the fastest thing in the universe, was going slower than a bike ride. This is the fourth mind-blown moment, and it challenges everything you think you know about light. But here's the thing. Light wasn't actually going slower. The speed of light is always 299,792,458 meters per second. That's an invariant constant. What Lean Howe slowed down was the group velocity of light in a medium. Let me explain the difference, because it's crucial to understanding what's actually happening. In water, light travels at about 75% of light speed. In glass, it's about 67%. But what Lean Howe did was more extreme. She used a phenomenon called electromagnetically induced transparency, discovered by physicist Stephen E. Harris. In her experiment, she had a cloud of ultra-cold sodium atoms at near absolute zero temperatures. She sent laser light through this cloud, and the group velocity slowed to 38 miles per hour. Then in 2011, scientist Andrew Zettel slowed light to just 2 inches per second inside a graphene oxide paper. But wait, there's something even stranger. In 2012, physicists at MIT somehow managed to stop light completely. Not slow it down, actually stop it. They stored light in a crystal structure and made it stay there. No movement at all. The photons existed in a state of quantum limbo, frozen in time. This is where we touch on some of the weirdest quantum physics. A photon can be absorbed by an atom, exciting the electron to a higher energy level. The photon ceases to exist as a traveling particle. It becomes encoded in the atom as potential energy. Later, that atom can release that energy as a photon again. So in a sense, light can be stored inside matter. And if you can store it, you can keep it there for as long as you want. Think of it like this. Imagine a conversation between two friends. One person speaks a sentence, then the other person thinks about it for a while before responding. The conversation doesn't end just because there's a pause. The words are still meaningful, still present in consciousness, even if they're not being spoken. That's similar to what happens when a photon is absorbed by an atom. The message, the information that light carries, is encoded in the atom, waiting to be re-emitted. Physicist Ronald Gamble at Clemson University took this even further. In 2007, he demonstrated that light could actually reverse direction in a metamaterial. Light going into the material would re-emerge traveling backwards, defying the apparent one-way nature of light propagation. This was mind-bending because it suggested that the direction of light is not as fundamental as we thought. But here's the crucial point. In all of these experiments, the speed of light in vacuum never changed. The cosmic constant c never varied. What changed was how light interacted with matter. We discovered that light could be manipulated, delayed, redirected, even temporarily stopped. But the fundamental speed limit of the universe, the speed at which causality itself travels, remained inviolate. This leads us to one of the deepest questions in physics. If light can be slowed down, if it can be stopped, if it can be made to go backwards through metamaterials, what does that tell us about the nature of light itself? Light is not just a wave traveling through space. Light is the manifestation of electromagnetic force, one of the four fundamental forces of nature. When we slow light, when we manipulate it with matter, we're actually engaging in a conversation between electromagnetism and the quantum states of atoms. We're showing that the universe is far more interconnected, far more interactive than a simple image of light zipping through empty space would suggest. Physicist Ernst Mach said, "The universe is not made of matter. The universe is made of events. Every interaction between light and matter, every photon absorption and emission, every quantum field fluctuation, these are the events from which reality is constructed. The speed of light is the rate at which these events can influence each other. We're now halfway through our journey into the mind-bending truth about light. So far, we've learned that time moves at different speeds for different people. Space gets shorter when you move fast, and light itself can be slowed, stopped, and even reversed in exotic materials. But the truly profound implications are still coming. In the next section, we're going to explore something that sounds like pure fantasy. We're going to talk about whether the future is already written. We're going to discuss how the speed of light creates something called the light cone, which determines your entire possible future. And we're going to confront the possibility that you're free or might be an illusion. This is where we move from, wow, that's interesting, to oh my God, this fundamentally changes how I understand my existence. If you're not subscribed yet, please hit that button now. You're about to encounter ideas that most people never think about, and I want you to come with me for the full journey. Drop a comment with what country you're watching from, if you haven't already. I'm genuinely amazed by the global community watching this. Imagine that I'm standing right here, right now. The present moment is a single point. From this point, I can influence anything within a sphere expanding outward at the speed of light. This sphere represents everything I could possibly affect by sending a signal or traveling to that location. This is called my future light cone. Similarly, I can be influenced by anything within a sphere, contracting inward at the speed of light. This represents my past light cone, everything that could have influenced me. And here's the absolutely mind-bending part. Everything outside these light cones is causally disconnected from me. Events outside my light cones cannot possibly affect me, and I cannot possibly affect them. Not now, not ever, no matter how many years pass. This is the fifth mind-blown moment, and it's the foundation of something called the relativity of simultaneity. Two events might happen at the same time, according to one observer, but at different times according to another observer, moving at a different speed. There is no absolute now in the universe. Simultaneity is relative. Physicist Hermann Minkowski, one of Einstein's former teachers, showed this geometrically in 1908. He created what we now call a Minkowski diagram, which plots space on one axis and time on another. And he showed that the universe is actually four-dimensional, 3 spatial dimensions plus 1 temporal dimension, all woven together into spacetime. The speed of light determines the geometry of this spacetime. It's the ratio that connects space and time. Now let me blow your mind with what this actually means for your life. Right at this moment, there are events happening across the universe that you will never know about, that you can never influence, that might as well not exist as far as you're concerned. A star exploding in a distant galaxy, an alien civilization being born, events unfolding in the far reaches of space, you're causally isolated from them. The light from those events hasn't reached you yet, and it might take millions of years. But here's what's truly strange. If you accept that the light cone is fundamental, if you accept that the present moment is different for different observers, if you accept that causality is the fundamental principle of the universe, then you must accept something that sounds like science, fiction, but follows directly from Einstein's mathematics. Future events are, in a sense, already determined. Not by fate, not by a predetermined script, but by the structure of space-time itself. The universe at your future light cone, everything that will become your present moment eventually, already exists in the same sense that your past already exists. The events of your life are not being created as you live them. They're being revealed as your consciousness moves forward through time. This is called the block universe theory, and it's a direct consequence of special relativity. Physicist Roger Penrose, one of the greatest physicists alive, has written extensively about this. He showed that if relativity is true, and we have enormous evidence that it is, then time is not passing. You're not moving through a flow of moments. Rather, all moments, past, present, and future, exist equally in the four-dimensional block of space-time. Your subjective experience of moving from past to future is a strange quirk of consciousness, not a feature of the universe. Think of it like this. Imagine a movie reel. The entire film exists at once, all frames from beginning to end, simultaneously. When you watch the movie, you experience it frame by frame, from past to future. But the frames don't come into existence as you watch them. They already existed on the reel. Your consciousness is like a projector, moving from frame to frame, creating the subjective experience of time flowing. But the film space-time is all there at once. This is deeply unsettling for people who believe in free will. If your future already exists in the block universe, does that mean your choices are already determined? That you have no real choice? The answer is subtle. Your future choices exist in space-time, yes, but they're not determined by something external to you. They're determined by you. The actions you take in the future are part of the space-time structure, and they're part of it because you will choose to take them. There's no contradiction between a block universe and free will. Both can be true simultaneously. Physicist Carlo Rovelli has written beautifully about this in his books. The order of time and reality is not what it seems. He points out that Einstein never actually discovered relativity in a mystical sense. Einstein discovered it by sitting down and taking seriously the mathematics of how light behaves. The mathematics led to startling conclusions about the nature of space and time, and the mathematics has been confirmed by thousands of experiments. GPS satellites prove the block universe is correct. They have to account for both time dilation and the gravitational warping of spacetime. If you don't include these relativistic effects in the calculations, the GPS will be wrong by kilometers within hours. The universe does not care about our philosophical preferences. It does what the mathematics predicts. And the mathematics is built on the speed of light. The speed of light is the ratio that connects space and time in the Lorentz transformations. Change the speed of light, and the geometry of spacetime changes. Make light slower, and spacetime becomes more curved. Make light faster, and spacetime becomes more flat. The speed of light is literally the metric by which the universe measures itself. I can feel your mind stretching right now. We've gone from light is really fast to your future might already exist in a block of spacetime. This is the kind of profound philosophical shift that the speed of light initiates. But we're not done yet, not even close. In the next section, we're going to explore one of the most bizarre predictions of Einstein's equations: wormholes. Yes, actual wormholes might be possible. Einstein and physicist Nathan Rosen discovered them in 1935. We're going to talk about what they are, whether they might actually exist, and whether they could theoretically allow faster-than-light travel in a way that doesn't violate relativity. This is where we bridge the gap between what Einstein predicted and what the universe actually has. Because the more we study the universe, the more we realize that Einstein's equations are not just abstract math, they're a description of reality. And reality is far stranger than most people realize. If you could travel from one point in the universe to another instantly, what if you could fold space-time like a piece of paper, poke a hole through it, and create a shortcut? What if the universe itself contains tunnels through space-time that connect distant regions? This is not science fiction. This is the direct prediction of Einstein's theory of general relativity. In 1935, just 16 years after Einstein published General Relativity, he and physicist Nathan Rosen discovered something in the mathematics. They found that black holes, those regions of space-time so curved that nothing can escape, might connect to other regions of space-time through a tunnel. They called it an Einstein-Rosen bridge. Today, we call them wormholes, though Stephen Hawking coined the term to describe the structure more accurately. This is the sixth mind-blown moment. Wormholes are theoretically allowed by the laws of physics. They might actually exist. And if they exist, they might allow you to travel between distant regions of the universe far faster than light could carry you through normal space. Not faster than light technically, but using less time to get somewhere because the distance itself is shorter. Think of it this way. Imagine two distant cities separated by a vast desert. The fastest way to travel is still limited by how fast you can move through the desert. But what if you could tunnel under the desert and pop out on the other side? The tunnel path is shorter than the desert path, even though you're traveling through the tunnel at the same speed you'd travel across the desert. A wormhole is like that tunnel, but through space-time itself. Now, before you get too excited about wormholes as practical transportation, I need to give you the sobering reality. Physicist Stephen Hawking proved in 1974 that wormholes would likely collapse almost immediately. They would need exotic matter with negative energy density matter that pushes rather than pulls to stay open. We've never found exotic matter. We don't know if it even exists. In 1988, physicist Michael Morris and Kip Thorne, who won the 2017 Nobel Prize in Physics for his work on gravitational waves, investigated whether a traversable wormhole was theoretically possible. They found that yes, according to the math, it was possible. But it would require enough exotic matter to potentially have negative mass energy equal to the mass of Jupiter. And this exotic matter would need to be arranged very precisely in a very small region of space. The cosmic engineering project would be beyond anything a civilization could accomplish. But here's what's fascinating. The mathematics allows it. The laws of physics, as we currently understand them, do not forbid wormholes. And that alone tells us something profound about the structure of space-time. The speed of light creates a geometry where shortcuts through space-time are theoretically possible. Physicist Carlo Rovelli points out that the mathematics of general relativity shows that space itself is not fundamental. Space-time is not a vast empty container where objects move around. Rather, space-time is woven from the relationships between particles and fields. Distance itself is a derived quantity, not a fundamental one. If distance is not fundamental, then shortcuts through space-time wormholes are conceptually consistent with how the universe actually works. Now here's something truly mind-bending. If wormholes exist and allow travel from one space-time point to another, they might allow something that sounds impossible: time travel. Not to the future, we already know that's possible through time dilation. But what about traveling to the past? A wormhole's two endpoints might not just be separated in space. They might be separated in time. You could enter one mouth of the wormhole and exit the other mouth at an earlier date. Physicist Igor Novikov and others have studied this and concluded that closed time-like curves paths through space-time that return to their starting point in the past might be possible if wormholes exist. But here's the thing. Every analysis shows that causality paradoxes are avoided by the Novikov self-consistency principle. If you travel back in time, The universe constrains your choices so that you cannot create a paradox. If you tried to kill your grandfather before he had children, you would fail. Your gun would jam. You'd miss. Something would prevent the paradox. The mathematics suggests that the universe is self-consistent and causality is preserved. This suggests something profound. The speed of light is not just the speed limit for traveling through space. It's the fundamental principle that preserves causality and consistency in the universe. Try to violate causality, and the universe prevents you. That's not arbitrary. That's the structure of space-time itself. We've now explored some of the most mind-bending implications of the speed of light: time dilation, space contraction, slowed light, the block universe, and wormholes. We've moved from light is the fastest thing to the speed of light is the fundamental constant that determines the shape of space-time and the nature of causality. But we're about to enter the territory of the truly bizarre. In the next section, we're going to talk about quantum entanglement. We're going to discuss how two particles can be connected in ways that seem to violate the speed of light limit, except they don't. We're going to explore whether quantum mechanics and relativity can be unified. And we're going to confront one of the deepest mysteries of physics. What does the speed of light actually mean at the quantum level? This is where relativity meets quantum mechanics and things get absolutely weird. Drop a comment if you've ever wondered whether quantum entanglement could be used for faster-than-light communication. We're about to explain exactly why that's impossible. And thank you for sticking with me this far into this journey. Your engagement and comments drive us to make more content like this. Here's a question that has baffled physicists for decades. Can information travel faster than light? And if two quantum particles are entangled connected by a quantum correlation that can span any distance, and a measurement on one instantly affects the other, hasn't information traveled faster than light? This is where the speed of light meets quantum mechanics. And the answer is both yes and no, depending on how you define information. Physicist John Bell proved in 1964 that quantum entanglement is real and cannot be explained by any hidden variables. Later, Alling Aspect performed experiments in 1982 that confirmed Bell's theorem. Since then, thousands of experiments have proven that entanglement is genuine. But here's the crucial point. Entanglement cannot be used to send information faster than light. And that's the seventh mind-blown moment, because it shows that the speed of light is protected by something even deeper than we thought. Think of it like this. Imagine you and a friend have two magic coins. You each take one. When you flip your coin, it's random heads or tails with 50-50 probability. But here's the magic. Whenever you flip heads, your friend's coin always lands tails, and vice versa. The outcomes are perfectly correlated, no matter how far apart you are. But you cannot use this correlation to send a message. Your coin is still random from your perspective. Your friend's coin is still random from their perspective. It's only when you compare your results that you see the correlation. Physicist Erwin Schrödinger, who formalized quantum mechanics alongside Werner Heisenberg and Paul Dirac, called entanglement spooky action at a distance. He was deeply troubled by it. It seemed to violate the principle that nothing can travel faster than light. But Schrödinger was also the one who realized that entanglement does not allow faster-than-light signaling. Here's why. When you measure your entangled particle, you get a random result. There's no way to control that result. You can't make your particle land heads if you want to send a message. Your result is fundamentally random. Your friend measures their particle and also gets a random result. From their perspective, they have no way to know whether you've measured your particle or not, because your measurement doesn't change the apparent randomness of their results. It's only when you compare notes, when you communicate through a normal, light-speed limited channel, that you see the correlation and confirm the entanglement. This is a profound principle in physics called the no-communication theorem. It's the universe's way of protecting causality. Quantum mechanics allows correlations that seem to act instantly, but those correlations cannot be used to send information. Causality is preserved. Physicist David Deutsch formalized this in the context of the many worlds interpretation of quantum mechanics. In this interpretation, every quantum outcome happens in a parallel universe. When you measure a quantum particle and get a result, the universe branches. In one branch, you got heads. In another branch, you got tails. Both outcomes happened. The entanglement between your particle and your friend's particle ensures that in the branch where you got heads, your friend will definitely get tails when they measure. But from your perspective, you don't know whether you're in the heads branch or the tails branch until you see your result. And the correlation doesn't become apparent until you compare notes through normal communication. The speed of light is not just a limit on how fast information can travel. It's the foundation of quantum mechanics' consistency. It ensures that causality is preserved even in a world where particles can be entangled across vast distances. Now, here's something that blows my mind every time I think about it. Physicists have discovered that quantum field theory, the most successful theory of physics we have, which explains 3 of the 4 fundamental forces, can be derived from principles about causality and the speed of light. Physicist Juan Maldacena discovered something called ADS-CFT correspondence, which suggests that gravity and spacetime might emerge from quantum information at a lower dimensional boundary. It's incredibly abstract, but the implication is stunning. Spacetime itself, including the speed of light, might be an emergent phenomenon. The speed of light might not be fundamental. It might be the way the universe encodes quantum correlations into the structure of space and time. This is speculative, cutting-edge theoretical physics, but it suggests that everything we've discussed, time dilation, wormholes, the block universe, might all be consequences of even deeper quantum principles that we don't yet fully understand. The speed of light might be the signal of a deeper layer of reality that we're only beginning to comprehend. We're now at a point where we've explored not just the speed of light as a physical constant, but as a principle that protects causality and consistency in both relativity and quantum mechanics. The speed of light is not arbitrary. It's the universe's way of ensuring that cause comes before effect, always. But in the next section, we're going to shift gears dramatically. We're going to move from theoretical physics to observational astrophysics. We're going to talk about real objects in the universe that are defined by the speed of light, black holes. We're going to discuss how black holes are objects where space-time is curved so extremely that even light cannot escape. And we're going to explore one of the most recent discoveries in physics, gravitational waves, which travel at the speed of light and gave us a completely new way to observe the universe. We're moving into the realm of actual observations and measurements. The things we're about to discuss are not hypothetical. They're real phenomena that we've detected with instruments. And they prove that everything we've talked about so far is not just mathematics. It's the actual structure of the universe we live in. Keep watching. The next sections are where theory becomes reality. In the center of almost every galaxy in the universe, there exists an object so extreme, so weird, so fundamentally wrong, that for decades most physicists refused to believe it was real. A black hole, an object where space-time is curved so extremely that the escape velocity exceeds the speed of light. Once you cross the event horizon, the point of no return, not even light can escape. A black hole is what happens when you squeeze all the mass of the sun into the size of a city. The density is incomprehensible. A teaspoon of neutron star matter would weigh as much as all the cars in the world. But a black hole is even more extreme. A black hole is what happens when matter is compressed beyond even the neutron star stage. Physicist Carl Schwarzschild worked on Einstein's general relativity equations in 1916, just 1 year after Einstein published them. He found an exact solution to the equations that described a spherically symmetric mass. This is now called the Schwarzschild solution, and it's the foundation of all black hole physics. The radius of the event horizon of a black hole is called the Schwarzschild radius. For a black hole of 1 solar mass, the mass of our sun, the Schwarzschild radius is about 3 kilometers. The entire mass of the Sun would fit inside a sphere 6 kilometers in diameter. The density would be 2 billion tons per cubic centimeter. For a supermassive black hole at the center of our galaxy with 4 million solar masses, the Schwarzschild radius is about 12 million kilometers. That's larger than the orbit of Mercury. The density is much lower, even though the black hole is more massive. This is the 8th mind-blown moment. As black holes get more massive, their density at the event horizon actually decreases. You could theoretically fall through the event horizon of a supermassive black hole without noticing anything special in the moment. But once you crossed it, your fate would be sealed. You would inevitably approach the singularity at the center, where density becomes infinite and the laws of physics as we know them break down. For decades, black holes were purely theoretical. Physicists argued about whether they could actually exist in nature. But in 1971, astronomers discovered an X-ray source in the constellation Cygnus. They named it Cygnus X1. It was in orbit around a blue supergiant star, and something was pulling material off the star. The material was heating up and emitting X-rays. All the observations were consistent with a black hole. But the smoking gun came much more recently. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected gravitational waves for the first time. Two black holes had spiraled into each other and merged, and the collision had been violent enough to create ripples in spacetime itself. These ripples traveled at the speed of light across billions of light years and were detected by exquisitely sensitive instruments. Rainer Weiss, Kip Thorne, and Barry Barish won the 2017 Nobel Prize in Physics for this discovery. And here's what's amazing. The gravitational waves traveled at exactly the speed of light, not faster, not slower. This confirmed Einstein's prediction that gravity travels at light speed. Since 2015, LIGO has detected dozens of black hole mergers. In 2019, another detector called the Event Horizon Telescope produced the first image of a black hole's shadow, the dark region where light cannot escape. It was the black hole at the center of galaxy M87, about 55 million light years away. The image showed a bright ring of light surrounding a dark center, exactly as Einstein's equations predicted. Scientists processed the image and found it consistent with a black hole of about 6.5 billion solar masses. The image was so iconic that it was broadcast around the world. Black holes reveal something profound about the speed of light. The speed of light is not just the fastest speed, it's the speed of causality itself. Inside a black hole's event horizon, the roles of space and time swap. This is hard to visualize, but imagine that in normal space, time is the vertical direction and space is the horizontal direction. Inside a black hole, space and time switch roles. Space becomes vertical and time becomes horizontal. This means that the future direction inside a black hole is the same as the direction toward the singularity. You cannot avoid moving toward the singularity any more than you can avoid moving into the future outside the black hole. The speed of light defines the structure of space-time so fundamentally that even at the edge of a black hole, where space-time is warped to the maximum before it becomes pathological, the speed of light is still the invariant constant that determines the geometry. Physicist Stephen Hawking discovered in 1974 that black holes are not actually black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation is caused by virtual particle-antiparticle pairs being created near the horizon. One particle falls into the black hole while the other escapes, carrying energy away. Over billions of years, black holes evaporate through this process. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. A small black hole would have high Hawking radiation temperature and would evaporate quickly. The supermassive black holes at the centers of galaxies would evaporate over timescales, much longer than the current age of the universe. But eventually, all black holes will evaporate away, their mass converted to radiation traveling at the speed of light, spreading their information back into the universe. There's a deep mystery here. If a black hole evaporates away completely, where does all the information that fell into it go? This is called the black hole information paradox, and it remains one of the deepest unsolved mysteries in physics. But whatever the answer is, it will involve the speed of light in some essential way. We've now journeyed from relativistic effects that you might experience in a high-speed spacecraft to the most extreme objects in the universe. Black holes are the laboratories where general relativity and quantum mechanics collide. They're the places where the speed of light becomes the boundary between the possible and the impossible. In the next section, we're going to explore the most recent revolution in physics, gravitational waves. We're going to discuss how we've learned to detect ripples in spacetime itself. We're going to talk about the next generation of gravitational wave detectors that will open up a completely new window on the universe. And we're going to discuss what gravitational waves tell us about the speed of light and the nature of gravity. This is where abstract theory becomes experimental reality. This is how modern physicists are probing the deepest mysteries of the universe. And gravitational waves have already given us insights that would have been impossible to obtain any other way. Drop a comment if you've ever heard of gravitational waves before. Tell me what you thought when you first heard about them. And seriously, if you haven't subscribed yet, this is the moment. We're building toward the most profound implications of the speed of light, and I want you to be here for all of it. On September 14th, 2015, the Laser Interferometer Gravitational Wave Observatory detected something that would change astrophysics forever. Two black holes had spiraled into each other and merged in a collision so violent that it sent waves rippling through spacetime itself. These waves had traveled for 1.3 billion years at the speed of light, and they arrived at Earth with a signal that lasted less than a second. For a fraction of a second, these gravitational waves had more power than all the light emitted by all the stars in the visible universe. Yet they were so weak by the time they reached Earth that detecting them required instruments of extraordinary sensitivity. LIGO had to measure changes in distance smaller than the width of a proton. It's like measuring the distance to the nearest star and being able to detect a change smaller than the width of a human hair. This is the ninth mind-blown moment. We have successfully detected the fabric of space-time itself rippling. We can hear the universe. We have opened an entirely new sense through which to observe the cosmos. Think of it like this. For 400 years, since Galileo invented the telescope, we've observed the universe using light. Visible light, infrared, ultraviolet, X-rays, gamma rays, all electromagnetic radiation. But electromagnetic radiation is only one way the universe communicates. Gravity is another. And gravity travels at the speed of light. So gravitational waves are another manifestation of the speed of light limit. It's the speed at which the universe can propagate the effects of massive objects moving through spacetime. Gravitational waves are produced when massive objects accelerate. A spinning neutron star, orbiting black holes, or the collision of two massive objects can all produce gravitational waves. These waves stretch and compress spacetime as they propagate outward at light speed. They carry information about the masses, spins, and velocities of the objects that created them. Einstein predicted gravitational waves in 1916 as a consequence of his general relativity equations. But for decades, no one could figure out how to detect them. The effect is incredibly tiny. The acceleration of massive objects occurs in deep space, billions of light years away. And by the time the waves reach Earth, they've been attenuated enormously. It took decades of technological development to build LIGO. Rainer Weiss conceived the laser interferometer approach in the 1970s. He had to solve problems like how to isolate the detector from vibrations, how to get enough light to measure tiny changes in distance, how to reduce quantum noise. In 1992, the National Science Foundation approved funding to build the first LIGO detectors. Scientists like Kip Thorne and Barry Barish worked to refine the design and recruit the international collaboration of scientists who would make the first detection possible. When LIGO finally detected the gravitational waves from merging black holes in 2015, it confirmed one of the last unverified predictions of general relativity. It opened up a new way to study the universe. In 2017, LIGO detected gravitational waves from merging neutron stars for the first time. This event was also observed by electromagnetic telescopes around the world, confirming that the neutron stars had collided and produced both gravitational waves and light. Here's what's absolutely crucial. The gravitational waves and the light from the neutron star merger arrived at Earth within a few seconds of each other. They had traveled 130 million light years, and they arrived with only a 1.7-second delay between them. This proved that gravitational waves travel at the same speed as light. The speed of light is not just the limit for electromagnetic radiation. It's the limit for gravity itself. This might sound like a minor detail, but it's actually profound. If gravitational waves traveled at a different speed than light, it would require modifications to Einstein's theory of general relativity. It would suggest that gravity is propagated by some unknown mechanism different from the curved spacetime that Einstein described. But gravitational waves travel at the speed of light, which confirms that Einstein's picture is correct. Gravity is not a force in the Newtonian sense. Gravity is the curvature of spacetime. The speed of light is the fundamental constant that determines how quickly this curvature can propagate. Physicist James Clerk Maxwell unified electricity and magnetism in the 1860s, showing that they're two aspects of the same electromagnetic force. Light is a manifestation of this unified field. Einstein unified space and time into spacetime in 1905. Then he unified gravity with geometry of spacetime in 1915. Now, physicists are working to unify gravity with quantum mechanics, and the speed of light is the key to understanding how these unifications are possible. Every detection of gravitational waves by LIGO and other detectors is a confirmation that the speed of light is the fundamental speed limit of the universe. Every gravitational wave we detect is carrying information that traveled at light speed. Every black hole merger we observe with gravitational waves confirms that even at the extreme edges of physics, where densities approach infinity in spacetime is warped to near pathological conditions, the speed of light remains the invariant constant. We've now traveled from the theoretical predictions of relativity to the experimental detection of gravitational waves. We've seen how the speed of light connects time dilation, black holes, and the very fabric of spacetime. We've seen how gravity itself travels at light speed, but we're entering the most profound section of this entire journey. In the next section, we're going to shift from the physics to the philosophy. We're going to discuss how the speed of light profoundly changes how we see our place in the universe. We're going to talk about why the speed of light makes it almost impossible for technological civilizations to dominate the universe. We're going to explore the cosmic loneliness that the speed of light imposes on every conscious being. And we're going to discuss whether this cosmic isolation might actually be a form of mercy. This is where we move from, here are the amazing facts, to here's what it all means for you, for humanity, for the future of consciousness in the universe. We're at the halfway point of the emotional and philosophical journey. Stay with me. These last sections will change how you see reality. Imagine you are a curious civilization on a habitable planet around a nearby star. You develop technology. You start asking questions about the cosmos. You look up at the night sky and wonder, are we alone? You point radio telescopes at the stars. You send messages out into the void. And then you wait. The nearest star system is Alpha Centauri, 4.37 light-years away. A message traveling at the speed of light would take 4.37 years to get there. If an alien civilization received your message and responded immediately, it would take another 4.37 years for their response to reach you. You would be 8.74 years older by the time you knew anyone was listening. This is the 10th mind-blown moment. The speed of light makes the universe incomprehensibly lonely. Think of it like this. Imagine you send a message in a bottle into the ocean. Years later, someone finds it on a distant shore and writes back. They put their reply in a bottle and cast it back out. Years later, their message reaches you. By that time, you've changed. The world has changed. The original context of your message is gone. This is the fundamental problem of cosmic communication. Distances in space translate directly to delays in time. Physicist Michael Hart calculated in 1975 that if even one technological civilization had reached the stage where it could and wanted to colonize the galaxy, starting 50 million years before our time, the entire galaxy would already be colonized. The galaxy would be full of alien megastructures, artificial worlds, signs of engineering on a cosmic scale. Yet we see no signs of this. The sky is silent. This is called the Fermi paradox, named after physicist Enrico Fermi, who asked in 1950, "Where is everybody?" The most obvious answer is that the speed of light makes galactic colonization practically impossible. Imagine you're a spacefaring civilization. You want to explore the galaxy. Even if you could build spaceships that travel at 10% the speed of light, which would be an engineering feat far beyond our current capabilities, a journey to the center of the galaxy, 26,000 light-years away, would take 260,000 years. Civilizations rise and fall in a fraction of that time. Governments collapse, cultures change, populations drift apart. The outposts you establish become independent worlds. Eventually, they might forget that they came from Earth. They might become hostile to the home world. Physicist Freeman Dyson and others have speculated about technological civilizations that have achieved a kind of immortality by spreading across vast distances, with different parts of the civilization potentially becoming independent and evolving in different directions. But even these immortal civilizations are constrained by the speed of light. They cannot coordinate in real time across light years. They cannot form a unified government. They're isolated by the cosmic distances. This leads to a profound realization. If the universe contains intelligent life, it's almost certainly isolated. Civilizations separated by stars cannot have real-time conversations. They cannot form alliances quickly. They cannot wage wars on cosmic scales because coordinating the effort would take millennia. The universe, despite potentially being full of life, would be profoundly, tragically alone. Physicist Isaac Asimov called this the cosmic principle. He suggested that the speed of light might be nature's way of preventing any single civilization from dominating the universe. If faster-than-light communication were possible, a sufficiently advanced civilization could potentially control all of space. But the speed of light limit ensures that every world, every system, every conscious being must grapple with their own isolation. Philosopher Thomas Nagel has written about this in the context of the cosmic view. When you really contemplate your place in the universe, when you understand that the light reaching your eyes from distant stars took years, centuries, or millennia to arrive, and that you are separated from other possible civilizations by distances that make real-time communication impossible, you feel a kind of vertigo. You realize that your consciousness is isolated in space and time in a way that's almost incomprehensible. But here's what's beautiful about this loneliness. It might be what gives life meaning. If the universe were crowded with civilizations in constant communication, if we could instantly summon help from the advanced intelligences across the galaxy, would we even bother developing our own technologies, our own art, our own wisdom? The isolation imposed by the speed of light forces us to grow. It forces us to become self-sufficient. It gives us the freedom to develop in our own direction. Let me bring this down to a personal level. You are a conscious being on a planet orbiting a star. The nearest star is so far away that its light took years to reach you. The galaxies around us are flying away from us at speeds approaching the speed of light due to the expansion of the universe. The universe is so vast that the light from the most distant galaxies has not yet reached us. There are parts of the universe we will never be able to see because the universe is expanding faster than light can travel. You exist in an island of space-time, surrounded by cosmic horizons defined by the speed of light. Beyond those horizons, there might be entire civilizations, entire galaxies, entire realities that you can never know about. Your connection to the rest of the universe is limited by the finite speed at which information can travel. But here's the profound truth. This isolation is shared. Every conscious being in the universe faces the same limitation. An alien astronomer on a world orbiting Proxima Centauri is also isolated by the speed of light. They're looking out at a universe that's fundamentally unknowable in its totality. They're experiencing the same cosmic loneliness. And perhaps that's a point of connection. Perhaps the shared experience of being isolated by the speed of light, of being separated from the wider universe by cosmic distances, is what would unite different civilizations if they could ever make contact. Perhaps we would recognize in them the same wonder, the same loneliness, the same longing to understand that defines conscious life as we know it. We've now moved from the physics of the speed of light to the philosophy of cosmic isolation. We've explored how the speed of light shapes not just physics, but the destiny of civilizations and the meaning of consciousness itself. In the next section, we're going to bring this home even more directly. We're going to talk about time. We're going to discuss how the speed of light reveals something profound about the nature of time itself. That time is not fundamental, but emergent. We're going to explore how consciousness experiences time differently than physics describes it. And we're going to discuss whether the passage of time is an illusion or the most fundamental aspect of existence. This is philosophy meeting physics at the deepest level. This is where we question what time actually is and how the speed of light defines it. If you've been skeptical about some of the ideas we've presented, the next section is going to give you a new framework for thinking about them. Thank you for making it this far. We're in the home stretch now. The remaining sections will tie everything together and leave you with a perspective on reality that's fundamentally different from where you started. Let's go deeper. You experience time as a flow. The past is behind you, the future ahead of you, and the present is a moving point separating them. This experience is so fundamental to human consciousness that it seems obviously true. Time is passing. You cannot go back. You move inexorably toward the future. But modern physics suggests something radically different. The flow of time is an illusion. This is the 11th mind-blown moment, and it's one of the most unsettling ideas in all of science. According to Einstein's relativity, the past, present, and future all exist equally. There is no now that is privileged over any other moment. The present moment is just a pointer in space-time, and there's nothing fundamentally special about it. Physicist Michael Tooley calls this the B theory of time. The past didn't cease to exist. The future hasn't been created yet. They exist outside the flow of time, in the block of space-time, equally real to the present. Think of it like this. Imagine space-time is a four-dimensional crystal, with the three spatial dimensions and one temporal dimension frozen in time like a solid block of ice. Your present moment is a three-dimensional slice through this crystal. As you move forward through your life, your consciousness moves forward through the crystal, always experiencing the slice where it currently is as the present. But the entire crystal exists at once. All moments exist equally. Past, present, and future are not descriptions of what is happening. They're descriptions of where you are in the crystal. This contradicts our subjective experience so dramatically that most people reject it out of hand. But it follows directly from the mathematics of relativity, and the mathematics has been tested and verified thousands of times. Physicist Lee Smolin has argued that time must be real, that the block universe is wrong, that there must be something we're missing in how we think about physics. He points out that causality is fundamental. Causes must come before effects. But in a block universe, causation becomes something strange, not a process, but a pattern in the structure of spacetime. But here's the thing. Even Smolin acknowledges that the mathematics of relativity is extraordinarily accurate. It correctly predicts the results of experiments to astonishing precision. If the block universe is wrong, we haven't yet found the error in Einstein's mathematics. We might have to develop an entirely new theory of physics to replace relativity, and that theory would have to make all the same predictions that relativity makes. Physicist Lee Smolin and others have proposed alternatives, like the loop quantum gravity approach or the causal set theory. These attempt to build a quantum theory of gravity that preserves the notion of a flowing real time. But as of now, none of these alternatives have achieved the predictive power and experimental success of relativity combined with quantum field theory. The most unsettling part is this. The speed of light is intimately connected to the block universe. The speed of light determines the geometry of spacetime. If you accept the speed of light as an invariant constant, if you accept that causality follows light cones, then you're forced to accept that the block universe is the correct picture. The speed of light is the statement that all moments are equally real. It's the geometry of spacetime itself. Physicist Carlo Rovelli has written beautifully about this. He suggests that the flow of time is not a feature of the world. It's a feature of how we interact with the world. Our consciousness is a particular kind of system that is highly sensitive to entropy. We're made of matter and energy, organized in ways that are extremely unlikely. We lose information about the past and gain information about the future. This information gradient creates an arrow of time for us, even though the fundamental laws of physics are time symmetric. From the point of view of the entire universe, the laws work equally well in both directions of time. But from our point of view, embedded in a universe of extremely low entropy in the past and high entropy in the future, time has a direction. We naturally flow toward the future because that's the direction of increasing entropy. Here's how this connects to the speed of light. The speed of light determines which events can influence which other events. Events outside the light cone of your present moment cannot reach you. This creates a structure to spacetime. Your past light cone contains all the events that could have caused your current state. Your future light cone contains all the events you could possibly cause. The structure of the light cone creates a direction of causality that we experience as the flow of time. You cannot receive information from the future because that information would have to travel faster than light. You cannot change the past because you cannot influence events outside your future light cone. The speed of light carves causality into the structure of spacetime, and causality is what creates our experience of time flowing from past to future. In other words, the speed of light is not just the fastest speed in the universe. It's the foundation of how we experience time at all. Without the speed of light limit, causality would be violated. Without causality, there would be no arrow of time. Without an arrow of time, there would be no memory, no history, no consciousness as we know it. The speed of light is the thread that binds together causality, space-time geometry, and human consciousness. It's the answer to why we experience time the way we do. We've now journeyed from the physics of relativity to the philosophy of consciousness and time. We've explored how the speed of light creates the structure of causality, which creates the arrow of time, which creates the experience of consciousness. In the next section, we're going to take all of these threads and weave them into a coherent picture. We're going to discuss the implications of everything we've learned. We're going to talk about whether faster than light travel is truly impossible and what that means for humanity. We're going to discuss whether time travel to the future is possible while time travel to the past violates causality. And we're going to explore what the speed of light tells us about the ultimate fate of the universe. We're approaching the grand synthesis. After this, we're going to have the final 3 sections where we tie everything together and leave you with an expanded perspective on reality. You're almost to the end of this journey, and I promise you, the final sections are going to provide a sense of closure and meaning to everything we've discussed. Don't go anywhere. The best is yet to come. Here's something that has bothered physicists for over a century. Why is the speed of light 299,792,458 meters per second. Why that specific number? Why not faster? Why not slower? Is there some deep reason for it? Or is it just a cosmic coincidence? This is the 12th mind-blown moment, and it might be the most profound question in all of physics. Whether the laws of physics are unique and necessary, or whether they're arbitrary features of our particular universe. Physicist Paul Dirac discovered an interesting coincidence. If you calculate the ratio of the electromagnetic force to the gravitational force between an electron and a proton, you get a number. About why? Now, if you look at the ratio of the size of the observable universe to the size of an atom, you get almost the same number. This is called the large number coincidence, and Dirac was deeply puzzled by it. British physicist Brandon Carter observed another coincidence. The universe seems to be fine-tuned for the existence of life. If the strength of the electromagnetic force were slightly different, atoms couldn't form in the right way. If gravity were slightly weaker, stars wouldn't form. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. The constants of nature seem delicately balanced. This has led some physicists to speculate about the anthropic principle, the idea that the constants of nature must be compatible with the existence of life, because if they weren't, we wouldn't be here to observe them. The speed of light is one of these constants, and it's intimately connected to all the others. Here's what's truly strange. There's evidence that the speed of light might not be the same in all directions. This is called a violation of Lorentz invariance, and many physicists have looked for it. So far, no violations have been found. The speed of light appears to be isotropic the same in all directions. But the fact that physicists feel compelled to search for violations suggests that the universality of the speed of light is not philosophically obvious. It's an empirical fact that needs to be verified. What if the constants of nature are not truly constant? What if they vary slightly across space or time? What if the speed of light itself has changed over the history of the universe? Physicist João Magueo proposed a theory called variable speed of light cosmology, where the speed of light was much faster in the early universe than it is now. This theory could potentially solve some problems in cosmology without needing inflation. It's speculative and not widely accepted, but it shows that physicists are willing to question even the most fundamental constants. Think of it like this. Imagine the universe is a vast calculation being performed by some cosmic computer. The rules of the calculation, the laws of physics, are written in code. The constants of nature are the parameters of that code. The speed of light is one parameter. But who wrote the code? And why those particular parameters? This is where we encounter the deepest mystery. Why anything exists at all, and why it exists with the particular laws that it does. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in describing nature. Why should reality be describable by mathematics at all? Why should the universe obey laws that humans can discover and understand? This has led some physicists, including physicist James Gates at the University of Maryland, to speculate about whether the universe is actually a simulation. If the universe is a computation being performed by some advanced system, then the constants of nature are like the parameters programmed into the simulation. The speed of light would be the speed at which information can propagate in the simulation. Interestingly, there are mathematical structures in string theory and related fields that look like they could be error-correcting codes. Gates has found Adinkra symbols, which are mathematical structures used in error correction in classical computing, appear in the equations of supersymmetric geometry. Is this a coincidence, or is it evidence that the universe is encoded information? The simulation hypothesis is not yet science. It's philosophy. But it's taken seriously by some physicists and philosophers because it raises interesting questions about the nature of reality. If we lived in a simulation, what would that tell us? What would be different? Would the laws of physics be different? But here's the thing. Whether the universe is a simulation or not, The speed of light would still be the fundamental constant that determines how information can propagate. The speed of light would still be the cosmic speed limit. The speed of light would still be the foundation of causality and the arrow of time. Here's what all of this points to. The speed of light is not just a law of physics. It's something deeper. It's the way the universe encodes causality into the structure of space-time. It's the principle that prevents chaos and paradox. It's the foundation of logic and meaning in the universe. Without the speed of light limit, causality would be violated. Without causality, logic would be impossible. Without logic, consciousness would be impossible. The speed of light is not an accident. It's a necessity if a universe with consciousness, meaning, and logic is to exist at all. We've spent a lot of time on the physics, but now I want to bring this home to you personally. The speed of light is not just something that happens in distant galaxies and black holes. The speed of light profoundly affects your life right now, in ways you probably never realized. This is the 13th mind-blown moment, and it's about recognizing how deeply the speed of light is woven into the fabric of your existence. Let's start with the obvious. The light entering your eyes right now is traveling at the speed of light. The light from the sun took 8 minutes to reach you. In those 8 minutes, you have no knowledge of what's happening on the sun right now. For all you know, the sun could have exploded 8 minutes ago, and you wouldn't find out for another 8 minutes. You always see the sun as it was 8 minutes in the past. You live in a perpetual time lag with every object you observe. Think of it like this. The fastest possible information you can receive about any distant object is light. When you look at the moon, you see it as it was 1.3 seconds ago. When you see Mars, you see it as it was between 3 and 22 minutes ago, depending on the orbital positions. When you use radio to communicate with rovers on Mars, there's a delay of 3 to 22 minutes before you get a response. NASA has to program Mars rovers to be somewhat autonomous because real-time control is impossible. This principle extends to human communication. When you send a text message, it travels at nearly the speed of light through fiber optic cables, but it's not instantaneous. A text message around the world takes a fraction of a second. When astronauts on the ISS communicate with mission control, there's a 0.07-second delay. It's small, but it's real. The speed of light creates a lag in all human communication. But here's where it gets profound. This lag is inevitable. You cannot escape it. No technology can overcome it. Even if we develop quantum teleportation, which transfers quantum information instantly, or seems to the speed of light limit still applies, because you cannot use quantum teleportation to send a classical message faster than light. The mathematical structure of quantum mechanics is built on top of relativity, but the speed of light affects you in even more intimate ways. Let's talk about your brain. Your brain processes information by sending electrical and chemical signals along neurons. The speed of signal transmission along a neuron is about 100 meters per second. That sounds fast until you realize it's 3 million times slower than the speed of light. This means that consciousness itself is not instantaneous. When you see something, the light has to enter your eye, get converted to electrical signals, travel along the optic nerve to the brain, get processed by the visual cortex, and then be integrated with other information by your prefrontal cortex. This entire process takes about 300 milliseconds. By the time you're consciously aware of seeing something, it has already happened. This might seem to suggest that free will is an illusion. Your brain decides, and then your consciousness experiences the decision as if you made it. But think about it in terms of space-time. Your conscious experience and your neural activity are both happening in the present moment of your brain. They're causally connected. The decision and the consciousness are both part of the same pattern of neural activity. You are your brain's decision-making process, not some additional ghost observing what the brain decides. The speed of light limit on signal transmission in your brain creates this lag, but it's not a violation of free will. It's a feature of how brains work. The speed of light is not just an external limit on communication with the universe. It's intimately woven into the biological hardware of consciousness itself. Now, let's talk about what this means for your future. The speed of light creates hard limits on what kinds of technology are possible. Imagine trying to build a global computer network where all processing happens with minimal lag. Your latency is limited by the speed of light. Information traveling around Earth takes about 0.1 seconds. For applications requiring real-time coordination, this becomes problematic. Your brain processes information faster than light travels around the globe. This has implications for how technology will evolve. A global supercomputer connected by light-speed limited networks cannot have certain kinds of real-time coordination. Quantum entanglement cannot be used to overcome this limitation because it cannot transmit classical information. The speed of light will continue to constrain technological systems the same way, constrains the physics of black holes and stars. The future of technology might not be about defeating the speed of light, but about learning to thrive under its constraints. The most advanced technologies of the far future might be fundamentally different from what we imagine today, designed to work beautifully within the light speed limit rather than fighting against it. We've now moved from abstract physics to how the speed of light affects your biology, your consciousness, and your technological future. We've shown that the cosmic speed limit is not something that happens far away. It's woven into the fabric of your existence. In the final section, we're going to bring everything together. We're going to discuss the ultimate fate of the universe in light of what we've learned about the speed of light. We're going to talk about the heat death of the universe, the possibility of eternal expansion, and what it means for consciousness to exist in a universe governed by the speed of light. But before we get there, I want you to understand something. You are not separate from the universe. You are not an observer looking at the universe from outside. You are made of matter and energy that are subject to the same laws, the same constants, the same speed of light that governs everything else. When you understand the speed of light, you understand something fundamental about yourself. We're almost at the end of this incredible journey. One more section after this, and then we'll have our final wrap-up. Thank you for staying with me this far. Your engagement, your curiosity, your willingness to think deeply about these ideas, that's what drives content like this. Let's finish strong. We have arrived at the moment where everything converges. We started with a shocking revelation. Light is simultaneously the fastest thing in the universe and impossibly slow. We've journeyed through time dilation, black holes, gravitational waves, cosmic isolation, the nature of time itself, and the quantum foundations of reality. Now, I want to ask you the deepest question we can ask. What does it all mean? What is the speed of light ultimately telling us about the nature of existence, about our place in the cosmos, and about what it means to be conscious? This is the moment of synthesis. Everything we've discussed connects to reveal a profound truth about reality. Let me tie it all together. The universe is not a dead machine grinding along according to fixed laws. The universe is a conversation between possibility and actuality, between the quantum and the classical, between matter and mind. The speed of light is the voice of that conversation. It's the rate at which possibility becomes actuality. It's the speed at which the universe actualizes itself, moment by moment. Think of it this way. At every point in space-time, there are quantum possibilities fields fluctuating according to the Schrödinger equation, superpositions of states existing in a kind of potential reality. The speed of light determines how quickly these quantum possibilities can influence each other. It determines how quickly the universe can causally select which possibilities become actual. The speed of light is the rhythm of reality actualizing itself. Physicist John Wheeler called this the participatory anthropic principle. The idea is that the universe is not determined until it's observed, that consciousness participates in creating reality. This sounds mystical until you understand that observation in quantum mechanics doesn't mean a conscious being looking at something. It means any interaction that creates entanglement between a quantum system and the measuring apparatus. The universe emerges from quantum fields. These fields exist in superposition all possible configurations at once until interactions occur. Every interaction is constrained by the speed of light. Interactions at greater distances take longer to propagate. The causal structure of space-time ensures that causality is preserved. The speed of light is the speed at which these causal interactions can occur. In this view, the speed of light is not an external law imposed on the universe. It's the way the universe actualizes itself from quantum possibility to classical reality. It's the speed at which the universe becomes real. Here's what all of this points to. The universe is not random, but it's not determined either. The universe is actualization. It's the continuous process of possibility becoming reality. The speed of light is the rate at which that actualization occurs. And here's the profound realization. You are not separate from that process. Your consciousness is not an illusion or an accident. It's an integral part of how the universe actualizes itself. When you observe something, when you make a choice, when you create meaning through your thoughts and actions, you're participating in the actualization of reality. This is not mysticism. This is the direct consequence of quantum mechanics combined with relativity. The universe is not determined until the present moment. All possible futures exist in a superposition of potential outcomes. As you live your life, making choices, those choices collapse the wave function of possibility into classical reality. The future becomes actualized. In other words, the speed of light is the speed of becoming. It's the rate at which possibility becomes reality. It's the rhythm of existence itself. Now I want to tell you something that most physics classes will never mention. You are significant. Not in some trivial way, not in some false spiritual sense, but in a real, fundamental way. You are made of atoms that were forged in stars. You are made of matter that has existed since the Big Bang. The atoms in your body have been recycled countless times through generations of stars and planets. You are literally made of stardust. And that's not poetry, it's physics. When you understand the speed of light, when you grasp what it really means, you realize that you're not insignificant. You're one of the universe's ways of knowing itself. You're one of the points where the universe has reached sufficient complexity to be conscious. That's extraordinary. So here's what I want you to take away from this journey. The speed of light is not just a limit, it's a foundation. It's the principle that makes reality possible. It's the rate at which the universe actualizes itself from possibility into existence. You live in that universe. You are made of the same matter, governed by the same laws, limited by the same constants as everything else. When you understand this, when you really grasp it, you see yourself as part of something vast and profound and beautiful. The speed of light is both a limit and a promise. It's the limit that makes causality possible and a promise that the future is yours to create. You are not a passive observer of reality. You are an active participant in its actualization. Thank you for taking this journey with me. We started with a shocking revelation about light, and we end with a revelation about yourself. You are made of light. You are made of the same atoms that were created in the hearts of stars billions of years ago. The light that carried that revelation to your eyes traveled millions of years to reach you at this moment. You are not separate from the universe. You are the universe experiencing itself. You are the way the cosmos knows itself. If this video has changed how you see reality, and I hope it has, please do something for me. Drop a comment telling me which mind-blown moment hit you the hardest. Was it time dilation? The block universe? Gravitational waves? Black holes? I want to know which revelation resonated most deeply with you. Subscribe to this channel if you haven't already. This is the kind of content we make. Deep dives into the nature of reality, presented with scientific accuracy, but also with wonder and awe. We have an entire series on quantum mechanics, relativity, cosmology, and the frontiers of physics that you're going to love. And tell me, What country are you watching from? I've been asking throughout this video because I'm genuinely amazed at the global community that's interested in these profound questions about the nature of reality. Your comments help me understand who's listening and what resonates with people around the world. Finally, share this video with someone who loves science, someone who loves thinking about big ideas, someone who's curious about the universe. Let's build a community of people who are passionate about understanding reality at the deepest level. Thank you for watching. Thank you for thinking. Thank you for caring about these ideas. I'll see you in the next video. Keep questioning, keep wondering, keep actualizing the future.